Hey, IB Physics kids, Mr. Tima here, talking about section 5.5 of light waves, the last section of our waves stuff. And I don't know, looks like the Pink Floyd cover, but basically it's a prism there where light is entering and it's diffracting out into all of the different colors. Okay, so again, the ideas here are in your assessment statements. And here you go. Electromagnetic spectrum. Hopefully you know all about the electromagnetic spectrum. There is a great picture of it in your Hamper book on page 172. Also, I'm going to attach my physical science notes on the electromagnetic spectrum. It will be in your Schoology folder. It is a link to a little YouTube video that I made for the physical science kids. It's okay. It's okay to watch it. Doesn't mean you're a bad student. If you've forgotten about it, it might be a good little refresher. It's going to be about 5 to 10 minutes on the electromagnetic spectrum. So there you go. But you are supposed to, in this class, already know all about the electromagnetic spectrum. Okay? Because we need to understand something. There's a lot of stuff in your book. There's tons of stuff in your book on this. But I gave you like the Mr. Tima Cliff Notes version here, the things you need to know. So everything in blue and red here is super important for you to know. They tend to focus on visible light, 400 nanometers to 800 nanometers. So basically from red light to violet light or blue light, if you will. Humans interpret these as colors. Color is perceived, but wavelength is measured. Okay, so we see blue, but blue's like 700 nanometers, okay? All right, velocity of light in a vacuum is 3 times 10 to the 8th meters per second. Brightness is intensity of light is measured in watts per meter. That has to do with basically the amount of wattage of light over an area, which kind of makes sense, and we'll talk about that. So proportional to the square of the wave's amplitude. So intensity is proportional to the amplitude squared. Power is intensity times 4 pi r squared. So basically, intensity times the area. Well, this is the area, or excuse me, not the area of a, yes, the area of a sphere. I was going to say circle, but of a sphere. Because remember, the angle of incidence is equal to the angle of reflection. When light hits, we can't just worry about that direct angle, though. We need to worry about the entire sphere itself, because that light is going to scatter. Remember, why do we see color? Okay, well, the reason that we see color is because it is the only color that is reflected. So when you see something red, it's actually absorbing all the other colors except for red. Green, again, there you go. When you see purple, it's really because it absorbs everything but red and blue, and when it mixes, it becomes purple or violet, or as they say, magenta. Okay, this is the refraction of light. And that has to do with Snell's law, which we've already talked about a little bit in this chapter, which is the sine of the angle over the sine of refraction, okay? And the velocity there. But we need to expand this, okay? So this is our original equation, okay? But this is the ratio which equals the index of refraction. So if they say the index of refraction is, let's say, 0.1, that's this entire thing. So this entire ratio, N2 over N1, is 0.1. It's not like the top is 0.1 or the bottom is 0.1. This entire ratio, this component is 0.1. So maybe they gave you the angle of incident is 40 degrees, and they tell you the index of refraction is 0.1. Well, what is the angle of refraction? Well, you have you have basically the top part, this side, and now you just solve for this. Well, we also can equate that to velocity, because if these two are equal and these two are equal, then these two are equal. Okay, so the index of refraction is also equal to the velocity of those. All right, diffusion, depression, whichever way you want to say it. Okay, it comes in, bang, bang, it scatters that light. It's also known as diffraction as well. Here's a little example for you. Simple, not going to make you solve it, just an easy thing. Remember, since we're dealing with degrees, we have to be in degree mode. Other parts of this chapter, you have to be in radians. Okay, but for this, we're talking about light waves. We're in degrees because we actually have angles that are in degrees. Okay, internal reflection. Internal reflection is basically like a mirror. Think about it. If that light bounces off a mirror, it's going to bounce back. Okay, we see that all the time. But what if we want to transmit it? Well, all that we talk about is like fiber optics, which is the lines that they're putting in the ground right now. You can transmit light, energy, data, everything through fiber optics. You have to think about it as like a wire, but instead of just being a straight wire, like a metal wire, this is like a wire that, if you imagine, it's encapsulated in like basically kind of like mirrors. The tube is like a mirror tube, so that when we do it, it just scatters in there and it continues to move forward. Okay, there's nothing lost there. It kind of moves through like that. So we can see this with diffraction of light, back to Dr. Quantum, all that kind of stuff where we talk about, let's see what's written there. There we go. All right, but this idea of intensity and diffraction. Okay, first of all, the center part has the largest intensity and it kind of fades as it moves out from the intensity, kind of like with music and everything else. Here's an actual, here it is with sound. We talked about if a sound comes out, you'll have this idea where if it's scattered and diffracted out again, you'll have this idea where the constructive and destructive zones are. All right. We've talked about this with light with sunglasses earlier on in this chapter. The idea of polarization of light, where we can actually polarize or turn a slit to basically cancel out harmful light. All right. Well, it can actually happen with regular matter as well. So we have a little video here for you. I have a little, where is it? There it is. All right, so we check this out real quick. Let's put this down here. Okay, let's watch that one more time. So basically, this is a motor that's oscillating the string. This is oscillating in almost a circle. You can almost tell it's two different ways. It's oscillating it in a circle. So it's basically in the X and in the Y, kind of like our picture back here, okay, in the X and in the Y. And then what they do is they polarize it one time. They polarize it one time. Right there's the one polarization. So by polarizing it one time, it's only moving in what would be called we'll call it the X direction. So we're kind of, or we'll call it Y so it matches the picture. It kind of looks like this. And then they're going to polarize it one more time. And if we do a complete polarization, we get a flat line, okay, where it's not vibrating at all. This is just a piece. These two pieces, it actually was two pieces at one point, but there we go, just one straight line. So polarization, the idea of changing the angle of that light and angle in order to cancel it out. Again, here is it with an actual light wave. The strongest intensity is in the middle. It tends to spread out and diffuse, if you will. Okay. All of this is talked about in something called Moll's law. Okay. All right. Where amplitude times the cosine of that turn. Okay. So it's like the angle, that slit's being turned. So if intensity is equal to the amplitude squared, then basically we can manipulate these two formulas into what is Moll's law. Well, Moll's law is the overall intensity is equal to the initial intensity cosine the angle squared. Remember, cosine squared theta is really just cosine theta squared. Okay, you'll have to answer like one question on that. Okay, but they love to ask that. I'm not really sure why, but they do. There you go. There's our homework again for this. We're going to focus on the SOCUS problems. These are extra problems if you want extra practice. Okay, but these are what we're going to focus on for our homework. So again, until next time, we'll see you.